Okay, hi, Assalamualaikum and good day to students. Alright, so for today's video, we are going to discuss for tutorial 1 and tutorial 2 of FST209. Alright, so this particular PowerPoint slide list out the answers for tutorial 1 as well as tutorial 2, and I will further explain the question that you have highlighted to me yesterday. So please take note and please focus on what I explain in this particular video. Okay, so for tutorial 1 FST209, for question number 1, you need to convert the following from British unit to SI unit. So for the question number 1A, the area, you need to convert from 28 feet square to meter square. The answer is 2.60 meter square. And then 1B, velocity, the answer is 13.4112 meter per second. Don't forget about the unit. Alright, and then question number 1C, density is 1047.90 kilogram per meter cubic, followed by latent heat 220958.2102 joule per kilogram. Or if you want to simplify the answer, you can simplify because the value is joule. You can also simplify as 220.96, for example, kilojoule per kilogram. Okay, because this one is joule. This one, the unit is in joule. So if you want to simplify the value, you can simplify by moving 3 point. Okay, you can divide by 1000 so that you can put the answer as kilojoule. Okay, alright, and then 1E, viscosity is 0.0521 kilogram per meter second. And then for F, pressure, this one I believe we have discussed during our last physical class. It is 1.70 for 1 bar. And then 1G, heat transfer coefficient, this one is negative 44,934.6309 watt per meter square degree Celsius. Okay, when we have the value of negative here, meaning that the heat is being given off to the system. This one involving with the cooling, whereby for the hot material they are being cooled, so meaning that the heat is being given off to the environment. Okay, so you have highlighted how to settle for the problem of 1G. Okay, so for 1G, the first thing what you need to do is you need to write down the value is 827 BTU per feet square hour degree Fahrenheit. Alright, so the first thing first, what you need to settle is you need to convert the BTU. This particular BTU, you need to convert from BTU, you need to convert to watt. So before you can convert to watt, you need to check with your conversion factors that you have in the tutorial. It is not a straightforward where you can simply convert directly from BTU to watt. So what you need to do is you need to convert from BTU to joule per second, then only you can convert to watt. Alright, so that's why this one BTU, we have this BTU, and then followed by conversion of from BTU to joule, and then this one from joule we are going to convert to watt. Okay, we go one by one. Alright, so first thing first, we are going to, okay, this one I think you are going to confuse with this one. So I will erase this one first. Alright. Okay, we change that one. So from BTU to joule, then we have joule per second, then followed by conversion to watt. Okay, so this one from BTU. This is the method, the steps that you need to convert from BTU to watt. Okay, so first thing first, we convert from BTU to joule. Okay, and then after that, feet square. This one we are going to convert feet square. And remember, this one feet square, meaning that it is 1 square feet square. Okay, so that's why when we want to convert from feet square to meter square, the value for the meter square need to be squared as well. Okay, 0.3048 square meter square. Okay, and then after that we have this hour. Hour we need to convert to second. Okay, because if you look from the conversion factor, look for your conversion factor. Okay, sorry, my handwriting here is a bit untidy. Okay, if you look in your conversion factor, 1 watt equals to 1 joule per second. So there must be an involvement of time here. So that's why this particular hour you need to convert to second. Okay, so 1 hour equivalent to 3600 seconds. And then because the value now is degree Fahrenheit, okay, let me erase this one first. Okay, so since this one is BTU per feet square, hour degree Fahrenheit, this one degree Fahrenheit. So meaning this one is 1 degree Fahrenheit. So how you are going to convert from 1 degree Fahrenheit to degree Celsius? You need to use the equation that is being given to you from the conversion factor, whereby you have this one. Okay, I write down here. Okay, the temperature T degree Fahrenheit, okay, equals to 1.8 degree Celsius plus 32. Alright, so now we want to convert to degree Celsius. So what's happened here, this particular T, you need to change to 1 degree Fahrenheit. Okay, for example, this one, the value is 1 degree Fahrenheit. Okay, so 1 degree Fahrenheit. 1 equals to 1.8 times by degree Celsius plus 32. So bring over this 32 to over here. So it becomes 1 minus by 32. Okay, equals to 1.8 degree Celsius. So this one become negative 31. Okay, am I correct? Divide by 1.8 degree Celsius. So, degree Celsius become negative 31 divided by 1.8. Alright, so you should be able to get negative 17.22 degrees Celsius. So that's why you will get this particular value. Okay, 1 degree Fahrenheit. 1 degree Fahrenheit is equivalent to negative 17.22 degrees Celsius. Okay, last but not least, this one from the conversion factor over here. So that's why we bring it over here. 1 watt equals to 1 joule per second. Okay, this one is 1 watt per 1 joule per second. So because this particular second is at the bottom, alright, you need to bring it upward. You need to bring it up so that this one has become 1 watt second per 1 joule. So that's why we can cancel out this unit of second and second, joule, and it becomes only 1 watt. It becomes watt. So the answer is negative 44,934.6309 watt per meter square degree Celsius. Okay. Then we move on to question number 2. The answer for question number 2A, volume is 1059.44 feet cubic. And then for pressure is 4.06 pound force per inch square. And then question 2C, latent heat equals to 1010.37 BTU per pound. D, heat conductivity is negative 0.0386 BTU per feet hour degree Fahrenheit, whereby for the speed is 6.71 miles per hour. And last but not least, question 2F, petrol usage is 28.21 miles per gallon. Alright, so you asked to explain further about question 2D, heat conductivity. Again, this one involving with the, this one involving with the unit conversion from watt meter Kelvin to BTU feet hour degree Fahrenheit. So I think you might find a problem when you want to convert the value for the temperature over here. Alright. Okay, now so let's take a look one by one. Okay, so the the value given is 17 watt per meter Kelvin. And again, look at the unit conversion whereby 1 watt equals to 1 joule per second. Alright, so that's why we have this particular watt. When we want to cancel out this unit, 1 watt, okay, 1 watt is equivalent to 1 joule per second. This particular watt is at the top, whereby this particular watt should be at the bottom because we want to cancel out the unit of watt and watt. And this one is 1 joule per second. Joule per second, this one should be at the top. And then per second. Okay, and then we want to convert from joule to BTU. Look at your conversion factor as well. Okay, where does this come from? This one is actually 1 kilojoule equals to 0.9476 BTU. Okay, so because kilo is equivalent to 10 to the power of 3, so that's why I take out this particular kilo to become 1 times by 10 to the power of 3 joule equals to 0.9476 BTU. Okay, clear? Where do I get this 10 to the power of 3? Alright, then we are going to cancel out. So joule and joule can be cancelled out here. And then for second, you need to convert to hour because the unit, it requires you to have hour. So of course, you need to settle this particular timing. So second and second, this one 1 hour equivalent to 3,600 second. Don't mix up this one because previously I have some of your seniors where they write as 1 second equivalent to 3,600 hour, which is wrong. So you need to make sure that you look properly for the unit conversion, okay, and then the value as well, the value that belongs to the unit. Alright, so now we move on for the meter, okay, because now we want to settle one by one for this particular watt first. Okay, watt you need to convert to joule per second, then from joule then after that you need to cancel out the joule to become BTU, then this particular second you need to cancel out as well. Then for the meter, since the meter, the value given is the meter is per meter Kelvin, so it should be at the bottom. So that's why when we want to convert, the meter should be at the top. It is 0.3048 meter per 1 feet. Alright, so this one there is a no square, so you should not square the value of 3048. Okay, so this particular meter and meter you can cancel out. Okay, now this will be the most challenging part. Basically, the student, they are having problem when they want to convert for the temperature. Okay, so since this one is per 1 Kelvin, okay, this one meaning that it is 1 Kelvin equals to okay, what is the value for temperature of degree Celsius? You need to look for temperature conversion. Okay, for temperature conversion, whereby whereby for the equation, in order for us to convert from degree Celsius to Kelvin is very clear cut, whereby the equation is simply by T Kelvin equals to T degree Celsius plus 273.15. Okay, so if let's say I have 1 degree Celsius plus with 273.15, sorry, this one 15, so it becomes 274.15 Kelvin. Okay, so this one very clear cut. But then what about Kelvin? 1 Kelvin. 1 Kelvin, what is the value for temperature of degree Celsius? So this one you just need to bring over this particular 273.15 to your left hand side. Okay, bring it over here. So it becomes, for example, this one, 1 Kelvin minus by 273.15 equals to T degree Celsius. Okay, so this one, for example, we delete this one. So the value just 1 minus by 273.15, it becomes negative 272.15 equals to T in degree Celsius. So that's why we get this particular value. 1 Kelvin equals to negative 272.15 degrees Celsius. Okay, and then from this particular value, negative 272.15 degrees Celsius, you need to convert to degree Fahrenheit. How you are going to do that is by applying the equation that has been given to you, whereby the temperature conversion for degree Fahrenheit, T degree Fahrenheit equals to 1.8 times by degree Celsius is over here, negative 272.15 plus 32. Okay, so you should be able to get the value as negative 457.87 degree Fahrenheit. So that's why you will get this particular value. Okay, so at the end, you should be able to get the value of heat conductivity is at negative 0.0386 BTU per feet hour degree Fahrenheit. Alright? Okay, so that's for tutorial number 1. Then we move on for tutorial 2, FST209. Okay, this one I give you the solution first, then I will explain to you for the question that you have highlighted. For question number 1, mass of solution is 30 kilograms. Question number 2, quantity of canned tuna is 18,667 cans. Okay, because for this particular question, it involves with physical product. So you cannot have a point. You cannot write down as 18,666.6 cans. There's no such thing as 0.6 cans. So it's either you can round it up as 18,666 cans, or you can write as 18,667 cans. This particular answer is acceptable as long as there is no point, because you need to think logically how can a can is having a point. Okay, it's either you have one can or you don't have any can of tuna. Alright, then question 3, water mixture equals to 270.89 kilogram, and then for concentrated sugar syrup is 256.19 kilogram, and fruit juice solid is 472.91 kilogram. So this one is for question number 3. We are going to discuss after this. Okay, then question number 4, lean beef is 77.36 kilogram, beef fat is 10.3 kilograms, sea water is 12.34 kilograms, whereby question number 5, weight reduction is 60%, and question number 6, water required is 160 kilograms. Question 7, flow of cream is 465 kg per hour. Flow of skim milk is 5368 kg per hour. And then question number 8, you have water evaporated is equivalent to 3500 kg per hour. Addition of fresh juice is 1125 kg per hour. Production of final product is 2625 kg per hour. Okay, so now I will explain to you for the question that you have highlighted. We move on for question number 3. Okay, please take a look. This one is question number 3. Okay, this one, from the problem statement, you need to gather the information and draw a block diagram like this. Okay, and then put all the known information into each inlet and outlet. Identify inlet and outlet. So for inlet, we have water mixture and it is being noted as W. And then we have this X, fruit juice concentrate, another inlet. Okay, and then another one more inlet. So you have basically 3 inlets, concentrated sugar syrup, denoted by Y. And then to produce this particular water mixture, fruit juice concentrate, and this sugar syrup is to produce cordial. Alright, cordial, P is for product. Okay, please identify what are the composition of each inlet and outlet. Okay, so this one already, this particular information has been given in your problem statement in the tutorial. Okay. So now, the first thing first, what you need to do is you need to generate overall mass balance. Overall mass balance, whereby we have learned previously, is inlet equivalent to outlet. Okay, total mass balance in inlet equivalent to total mass balance in outlet. Alright, so we move on. Okay, so the basis, it has been given in the problem statement that we are going to produce 1000 kg of product. So, what will be the mass for each inlets that need to be added into the system in order to produce 1000 kg of product? So, the first thing first, you need to write down total mass balance. Total mass balance is whereby all the inlets, we have W, X, and Y equals to 1000. 1000, where this 1000 come from? This one. We want to achieve 1000 kg of product. Okay. And then what are the things that you find in common in this particular inlet and outlet? What are the things that you find in common? First, we have fruit solids. Okay. This one, we have fruit solids. This one, we have fruit solids. And then we have sugar. Sugar, sugar, and sugar. Okay, water only applicable in this particular W inlet. The rest, we don't have any water. So, don't use water, right? Use whatever composition that you have in common for each inlet and outlet. Alright, so the second one, mass balance for fruit solids. Okay, from the information given, 0.04W plus 0.4X. This one, where does it come from, 0.4X? This one is from 40%. Okay, 40%. 40% equals to 0.4, whereby 40 divided by 100. So, you will get 0.4. Okay, so that's why 0.04 plus 0.4X equals to 200. This particular 200 is 20%. 20% times by 1000, you will get 200. So, this one is the second equation. Okay, and then mass balance for sugar. This one is 0.15. Okay, can you see that? For total mass balance, we have 3 unknown, W, X, Y. Okay, and then for fruit solid, we have 2 unknown. Only 2 unknown, W and X. But for sugar, again, we have 3 unknowns. So basically this one is quite difficult because we have 2 equations with 3 unknowns and only 1 equation with 2 unknowns. Alright, so what happened here is 0.15W. This one is meant for best balance of sugar. 0.15W plus 0.85Y plus 0.3X equals to 4000. 4000 is coming from 0.4. Oh, sorry. It's supposed to be 400. It's not 4000. okay, 400, not 4,000. Because 0.4 times by 1,000 is supposed to be 400. Alright, and then this particular line is supposed to be here. This is the line. Okay, from equation number 2, from here, equation number 2, we simplify. We take out the unknown of x. Okay, x become to 200 minus by 0.04w divide by 0.4. Okay, x equals to 500 minus by 0.1w. This one is fourth equation. Okay, so this particular equation number 4, we substitute into equation number 3. Okay, why? Why do we do that? Okay, because equation number 3, we have 3 unknowns. Whereby equation number 2, we have 2 unknowns. So we want to reduce the unknowns, the number of unknowns in equation number 3 from 3 unknowns to become only 2 unknowns. Alright, so that's why the following step, we substitute equation 4 into equation 3. Okay, whereby the x value here, this particular x, we replace with this value. Okay, so this one, it has become this one. 0.15w plus 0.85 plus 0.3. This particular 500 minus by 0.1w, this one coming from this equation number 4. Okay, equals to 400. Okay, this one basically is from equation 3. This one is equation 3. But we replace this value, x, this value from equation number 4. Okay, so simplify this equation. Alright, then you will get y equals to 294.12 minus by 0.14w. This one equation number 5. Okay, so this one we have y, we have x. Okay, so we have 2 unknowns, so that's why substitute equation number 4 and equation number 5, okay, to equation number 1. We have x, okay, x, we have y, so the leftover unknown is only w. So you should be able to get the value for w when you substitute those equations. Okay, you have w plus 500 minus by 0.1 w. This one, where does it come from? This one is y. This one is x. This one is x. And then this one is y from equation number 1. And this one is 1000. Okay, equals to 1000. So 0.76w equals to 205.88. So you should be able to get w. Okay, w is 205.88 kilograms. And then y, just insert the value from y, this one, equation number 5. Okay, simply put here. We already knew the value for w. So this particular w, this value of w, plug in into this one, equation of number 5. This one is equation 5. Okay, substitute this particular w from here. Okay, then you should be able to get w is 256.19 kilograms. And then x, this one is equation from which equation? Equation number 4. Equation 4. Okay, plug in again. This one is the value for w. Okay, why do I choose equation number 5, equation number 4 to solve the problem for y and x? Because simply it has only one unknown. Okay, one unknown. W, this one also w. If you want to replace, you want to substitute the value of w in equation number 2, because this one you have x and w. It is also correct. It is not wrong, it's correct. But this one just a matter of, I already get a simplified equation, so why should I trouble myself to calculate for a more complicated equation? But you can do that. You can use equation number 2 because you already get the value for w. You can use this value and plug in into the equation number 2 to find the value for x. You can do that. It is not wrong. Okay? Right, so that one is question number 3. Now we move on to question number 8. Okay, question number 8, this one we have two systems. You need to know from the diagram has been given to you. You need to know that this particular diagram, it already given to you two separate systems. Okay, whereby it involves the first system. This is system number 1. The first system involving with evaporation. And then system number 2, okay, involving with mixing. So for system number 1, you will have total mass balance. You will have equation for system 1. System 1 is whereby you have total mass balance, okay, and then you have soluble solids. Soluble solids balance. Okay, and then equation for system number 2. Equation system 2. Again, you will have total mass balance. Because this one is a two separate system. Okay, and then we have soluble solids balance. Okay, clear? So we have this one is equation number 2, this one equation for number 1, system number 1. Okay, so for total mass balance, we have the value here, whereby we have this 5,000 kilogram per hour going into the evaporation system, 1 inlet. Okay, for system number 1, we have 1 inlet and 2 outlets. Okay, W and X is considered as the outlet for system number 1. Okay, and then for system number 2, how many inlet? We have X as the inlet for system number 2. We have F for the inlet of system number 2. And then we have Y for the outlet for system number 2. So you need to separate both system number 1 and system number 2. Alright? So how do we solve that? Actually, this particular problem is very simple, but then because it will confuse the student about these two systems, so that's why they will find it's quite difficult for them to solve the problem. But basically, it is simple to solve the question. Okay, so again, just now I've mentioned to you, you need to do total mass balance for system number 1. Okay, I write down as envelope number 1. This one actually for system number 1. Okay, 5,000 is from the incoming mass. Okay, 5,000 is incoming mass. The inlet for system number 1 equals to W plus X. W plus X is the outlet for system number 1. Okay, so this is the first equation. Okay, and then soluble solid mass balance for system number 1, soluble solid. This one we have already knew 15% times by 5,000. 15% of soluble solid is in the inlet. And then the outlet is 50% of soluble solid. W. Okay, W, this one, during evaporation. Evaporation, it will evaporate water. Okay, it only evaporates H2O. There will be no soluble solid going to be evaporated. So 100% of soluble solid will goes out from the channel of X. W is only meant for water. So that's why for soluble solid mass balance, we have 0.15 times by 5,000. This one is 15% of soluble solid in the inlet equals to 0.5, the 50% of mass of solids, soluble solids coming out from the channel of X. Then you will be able to get the value for X. X is 1,500 kilogram per hour. See, you already solved one problem. Okay. And then we move on for the system number 2. System number 2, we have X, inlet, F, inlet, and then Y as the outlet. So X plus F, X plus F, this one is inlet equals to Y. Okay, this one is equation number 3. whereby soluble solid mass balance for system number 2, this one again for X channel is 50% of soluble solid plus 15% of F is being added into system number 2, whereby we want to mix these soluble solids and this particular soluble solids. So the end product should have 35%, 0.35 of soluble solid in